Last class, we stopped right here. We stopped with the creation of mesh. Recall that we had created an elbow pipe, and then after creating elbow pipe, I closed the geometry model and then opened by right-clicking on the model. I opened edit, and then we had the ANSYS Mechanical Enterprise open. Once it opens, it will load the geometry, and then we went to mesh, right clicked on it and generated the mesh. Okay, so we do not make any, we do not enter any parameters for generating mesh. We just generate the default mesh that is created by the system. Once it is created, you will see below here on the toolbar some of the details. Okay. So let's just ensure I'm recording. Yes. So what are the details which are given? You will see that display, defaults, sizing, and some other information, quality of the mesh, inflation, advanced, and some statistics regarding the mesh are given there. If you go through the statistics, it gives you in this particular mesh how many elements are there. What do we mean by elements? If I zoom in here, let's see, let's say try to zoom in. I'm going to zoom in pretty well so that we can see how does the mesh look like. So you can see here this particular mesh element here. So this is one element. It is a 3D element, and you can see it looks like a block or a brick. Okay, brick in this case, but if I were to rotate this, okay, I think if I try to rotate, okay, if I were to rotate this and see the element inside, the shape of the element which is inside, you can see this particular element looks slightly different. It has 3 edges here. The element above had 4 edges. The element below here has 3 edges on the face. So the shape of the element is slightly different. Okay, so let's see here. So this is the element, and the total number of elements like these, there are about 8,385 elements. Okay, so why do we create these elements in finite element? In each element, we are going to calculate what is the deformation and what is the stress. So this way we will have what is the stress distribution over the length of the pipe or any structure here. There are about 51,866 nodes. If you pick each element, the corner points here, they represent one node. So each corner point represents one node. And like that, there are about 51,866 nodes. Okay, so all your calculations are done on the nodes of the element. Okay, except stress. For example, if I want to calculate what is the displacement at this particular location, then we in the finite element code, the displacement at each of these nodes are calculated. Okay, so that's how the entire calculation is done. Now we can also see the shape of the elements can be different. Some elements look like a wedge here. So when I say a wedge, what is the shape? Just 1 second. So what is the shape of the element in this particular case for a wedge? Let's draw the wedge-shaped element. I'm going to draw it approximately. So this is the shape of the wedge element. This is how it looks like. Brick element, on the other hand, will approximately look like a brick. So you have seen bricks. So this is a shape of a brick element. On the other hand, you may also have tetrahedral element. The tetrahedral element will look like a pyramid. Okay. So this is how a tetrahedral element looks like. So depending upon what kind of element you want, you can choose in the finite element program. But right now we are not going to choose. There are ways to control the type of element you choose. So let's see here if there is the element type given here. So here you can see element order and element size, two variables. We will also see about the element type later. So there are three type of elements you can create: wedge, brick, wedge, and E. Let me just connect my iPad before we continue. Otherwise, I will not be able to write. So 1 second. Okay. So let me write it. Here it is the brick element. Wedge element. And then tetrahedron. Okay. Now, suppose if I have nodes in each of these elements in the corners, it's called as the linear element. These are all linear elements. So the tetrahedral elements only on the corners. On the other hand, if I have more nodes, for example, in the center of the brick element here, then this becomes a second order element. Okay, so including the red nodes, if we also have the green nodes, then it becomes second order element. In the same way in the wedges. So there are different types of elements, different order of elements that can be created. So this one is brick. If it contains only the red, then we call this as linear element. And in addition to this, if we have the green nodes, then it becomes quadratic. If you want better solution, then we may need in some problems higher concentration of nodes. The more the number of nodes, the better the solution will be captured by the finite element solver. However, it will increase the number of unknowns and the time for solution can increase very much. So already we have seen here for the simple pipe problem, we have around 51,866 nodes, and each node will have displacement in 3 different directions. That means the total number of unknowns will be 3 times this value minimum. Suppose if you increase by giving the element order here as something different, linear, from linear to quadratic. Okay, in that case is going to increase the total number of nodes and control. There will be too many nodes and the number of unknowns will also increase. Okay, so generally it is okay if you leave it as program controlled. The program will automatically select what kind of elements it wants in each location, and then it will approximate the geometric surface. So leave it to the default size. Okay, in some cases you need to change it. Again, you can see here element size. You do not want to mess with this in general. There is also a resolution. If your particular mesh for your geometry doesn't work, you can increase the resolution and create much more concentrated mesh. So these are some control parameters. You can see here different types of control parameters are given. We will at a later time, when we have enough time, we will go through all these control parameters. Okay, so this is with regard to mesh. Okay, so let's zoom out and let's see here. No, we don't want to do this. And let's use the zoom out, the wheel. If you have the wheel in your mouse, you can zoom out by using the wheel, zoom in or zoom out. Okay, so we are back to our geometry. Let's deselect that by, let's see here. Okay, so we go to single select mode. Okay. All right, so what is the next step? Once we created the mesh, the next step in the solver is going to be prescribing your boundary conditions and any force that acts on the structure. So in this particular case of the pipe, let's think about some of the boundary conditions. Let's assume that we want to fix one of the surfaces at the edge here, or maybe we fix one of the edges. We will go with the surface. So if you look here, there are a couple of choices. The first one, smart select, it will select surface and edge, etc. based upon where you click. Okay. Let's see the other one. The other choice refers to a particular point, edge, and then we have surface. We want to select the surface, so I will go with the surface here. So I have already selected the surface. Since we want to select the surface, I want to zoom in so that I will be able to select the edge here. Okay. So I should be able to select the surface. I right click on the static structural here, insert. Okay, click on insert and then you can select any of the boundary condition. I want to fix the surface here. So I select fix support. Okay, and then you can see here geometry is highlighted. That means you need to first select the geometry. So let's select this edge. Again, if you recall, I enabled this particular button and then selected the edge, apply, and the edge is selected, and now it is fixed. Okay, so zoom out, pan, move it, and then we will be we can introduce other force conditions or any other condition we want. So let's see here. Let's keep this simple. Let us say that we have some force acting at one of the end. Yeah. Okay. We will assume the force is acting in the transverse direction to keep things simple. And let's rotate it and bring it to the other end so that we will be able to apply the force on this particular edge here. Okay. So let's select this, insert, and right click and insert, and then let's say, so we can either apply a pressure on the edges or a force on the edge. Okay, so we will go with the force. So let's select force. Again, the geometry is enabled. You can zoom in. To select this particular edge. So let's select this, apply, and then you are given what is the magnitude of the force. Okay, so let's see here. We are given it as a vector. Let's see here. So force vector. We can go by components. Okay, so either we can define the force as a vector and provide a particular direction to that, or we can directly specify components. We want to specify the components, and we want to give specifically, we want to give a particular direction for the force. Okay. If you recall, we extruded the pipe along the Z direction, which means most probably we want to apply the forces on X and Y. So keeping the Z component constant, maybe I want to apply some force in the X direction. Okay, so before doing that, we have to make sure our units are good. So first, let's go here and check the units. The unit system is meters, kg, newton, etc. Okay, so this is okay. We have the angles in degrees, the velocity in radians per second, everything is in SI units, and our temperature, since we do not have any temperature, we need not worry, but just in case, we have in degrees Celsius, or if we want, we can change it to Kelvin. So again, we can check all the units are in order, and then this is in units of newtons. So you can give any particular force. Let's say we apply a force of 1000 newtons or 1 kilonewton. Okay. And we can see immediately a graph is created where the force will be increased from 0 to 1. Okay, so what does this increase mean? This is a static problem. So why is the force increasing? In finite elements, the force will be applied in several steps. So we can think of this like the time axis, x-axis. It's not actually the time axis, but it is a pseudo time step. We can call it like a time axis, where the force will be increased in step. The number of steps involved here is only 1. So from 0 to 1000 newtons, it will be increased. And you can see the column time. It does not refer to the physical time, rather it refers to a pseudo time, because this is a static problem. We are not working on a time dependent problem. Okay, so this is not the actual time. You can think of it like a dummy time which is used within the finite element method. Okay, let's go back here. Y component, I want to apply, let's say, no, 2000 newtons. Okay, so this is all I want to do. So I have applied a force and a fixed support and a force. So let's see how the system behaves. So let's rotate now. And you can see the direction of the force. Sorry. No. So you can see the direction of the force here. Zoom out so that we can bring the pipe in particular direction. Let's see here. So this is the fixed end, looks like. Sorry. Okay, so this is the fixed end, or this is the force. Actually, this is the force. So we can see here red color shows the force. And if I click the other end, the fixed end is here, shown in the blue color. So these are the edges. You can adjust your zoom. Now you can see here a green tick mark. Whenever you get a green tick mark, means that part of the finite element analysis is done. What we need to do is get the solution here. And you can also see in the static structural system, you do not have a green tick mark here because it is still not done. All the parts are not done. Okay, so the next step, okay, let's see here. The next step, we click on the solution and we need to figure out what kinds of solution we want. Right click on it, press insert or just point to insert, and then look at the choices you have. You have deformation. Deformation means displacement. Displacement will be given. Either you will get the total displacement or you can get directional displacements. Okay, so we will opt for total displacement. I'm going to left click on it and total deformation appears. Again, right click. We just do not want only deformation. We want some information about stress. Okay. Now, since this is a 3D problem, you will have several stress components. If you have taken my solid mechanics course, you will know that there are 6 independent components, but you can combine these 6 independent components and come up with a single value for stress, which is called as equivalent stress. In finite element analysis, you will always come across what is called as the von Mises or equivalent stress. This stress determines whether failure will take place for a given material or not. Okay, so we can select this equivalent stress. Let's see if we have any other choices. And under the stress, you have the maximum principal stress, middle and minimum principal stress. In case if you want the principal stresses, you can select that as well. Okay, so let's see the maximum. Since it is a 3D, you will have 3 principal stress values. So middle and then minimum. Okay, so we saw all the principal stresses. We may also need some idea about the maximum shear stress. Okay, so you can select that as well. And let's further see again linearized stresses. What does this mean? Okay, the stress which is plotted here is the total stress when your component is deformed beyond the plastic limit or yield limit, then you will have two components of stress. Okay, one will be the elastic, due to elastic deformation, one component of stress, another one plastic stress. Okay, so let's see here. Before I go there, I can write a simple equation. So I can write the total stress plastic plus plastic. Okay, also the strain can be written as elastic strain plus plastic strain, especially if you have plastic deformation. So if you look at it from stress strain diagram, okay, this is the curve you have, and suppose that we are here. Okay, at this particular point, if you release, what will happen? The component will go back to zero stress here at this point, parallel to the initial line. And based on this, we can figure out what is elastic and the plastic strain. So this will be the elastic strain which can be recovered, and this will be the permanent plastic strain in the material. So this is what it refers to. Okay, so if you want only this component corresponding to this component, okay, what is the stress? Then you will be able to get that as well. But we are not going to select that. If you want, you can select. You will again have 6 different components here. There are other ones. You also have for the entire element, you can get what is the maximum equivalent stress if you want, the maximum shear stress, because the stress will vary at each of the points. Okay, so it will give for the entire pipe, elbow pipe here, the probably where it will give you the maximum equivalent stress along with the location in the same way here. So let's select, for example, here. Okay, all right, so we have the maximum equivalent stress. Where is it? I think the information will be given in terms of safety factor. Okay. Okay, so let's see here. Let's see, equivalent stress tool. It's giving you the safety factor. Let's point to this. Insert a stress tool based on the maximum equivalent stress failure theory. So basically, it gives you information regarding the failure theory which is applied. This is the von Mises-Henke failure theory, and therefore it gives you what is the factor of safety corresponding to von Mises theory. Okay, so let's go back here and look here. There are other tools here, probe, etc. We will see this once we get the results. Okay, so these are the results we want to get. What do? We go here and right click on static structural. We have the boundary conditions, forces along with the results we want. Now we solve for the system. Okay, so let's click here, solve, or you can directly click on the solve button over here. Okay, so click on the solve button. You can see here the progress of the solver, 50%, solving, writing results, file, etc. Now it is ready. Deformation is large, so some information is there. Let's see here. Show message. The deformation is large compared to the model bounding box. Verify boundary conditions are considered turning large deflection on. Refer to troubleshooting. Okay, so in this particular case, the force is too much, and because of that, we have very large deflection here. So let's see here. We do not turn large deflection on here, so we will come back to that part later. Maybe it's better we reduce the forces. Forces are too high for the system. Maybe we reduce it instead of having 500. The solution with these inputs. Okay, so let's solve the system again. You can see it's solving. Okay, so now it is okay. We do not have very large deflection in this case. The solution is fine. Okay, so let's see some of the results. We can go to the total deformation. We zoom out a little bit. So the total deformation shows on the left end, we do not have go to the select. So we do not have much deformation on the left end. Therefore, showing with the blue color, minimum deformation according to the color legend here. And as we go towards the right, the deformation is higher and higher, reaches maximum value towards the right end. Makes sense. Let's see the stress. In the case of stress, we see that there is maximum stress towards the fixed end, and on the other end, the stress is nearly zero. Okay, so here you can see these are the stress values, blue ones, versus here it reaches a maximum value. Similarly, we can get the maximum principal stress, the second value of the principal stress, and the minimum value of the principal stresses. And the distribution of these principal stresses are given at each of the points along the length of the pipe. You can also get maximum shear stress. Okay, so let us see here. Okay, so let's see here if we can. Okay, so that is, if you carefully take a look at it, in the beginning, we did not have this result tab. Once we solved for the particular elbow pipe, once we solved the system, then this new tab came here. Okay, so click on this tab. There are more choices given here. For example, you have this probe toolbar. Using the probe toolbar, we can figure out what is the maximum value of the result, minimum value of the result, etc. Okay, so let's check here. So let's see here how to work on it. I'm going to first zoom in. And let's pan out. Rotate a little bit. Again, pan. And let us say that I want to figure out on this surface here, particular surface, I want to figure out what is the maximum stress. So if I click on it, immediately it shows the point where the stress is maximum. So you can see here. Okay, so what is the maximum value? Let's see here. It gives you the maximum value here. Okay, so if I click on the probe button here, okay, and if I move my cursor around, you can see it gives you the values. Okay, so I don't want that. Okay, so let me just click here and gives you the maximum value 1.2294. Okay, so this is at a different location, not exactly at that location. Let's go here to the particular location and click on it. Okay, now it gives you right at that point what is the maximum value of the stress. Okay, so I can deselect probe, and suppose if I do not want the information displayed, let's see here, go back to the mode, use single select, and I do not want this particular probe to be displayed. Let's see, is there any way to delete it? So right now I cannot see the value for deleting. Okay, so let's see here. Doesn't allow me. Let's take the maximum value. It is displaying here. Okay, maybe with the probe value. No. Okay, so I'll come back to this later on how to delete any probe value which you have highlighted here. So using probe, at least we can display what are the stress values. Using the maximum or the minimum value, we can figure out where the stresses are maximum or minimum. Okay, so here again, if I want the minimum value displayed, let's see here. Okay, single select. So for the object, I think it is selecting for the entire object, where is the maximum and the minimum value. Let's rotate and see if the minimum value is given on the other end. Okay. So let's select now, and you can see the minimum value of the stress given here. So if you want the value, you can zoom in and pan to the particular location and try to get the value from that location. Okay, so this is again going to the wrong point. Okay, so let's go to the particular point here and click, and you will get what is the minimum value close to that location. Okay, so now we can zoom out, pan to get the model in place. Okay, so let's see. Okay. Okay, so this is how we get the information. There are additional functions as well. I will do this, probably the additional functions I will describe. Maybe you will be able to cut through the pipe and look at the stresses on the cut section, cut cross section. You can cut it horizontally along the length of the pipe or across, and you will be able to get the stresses for this particular case. So we are done for now. We are done with the elbow pipe model. So here what I have shown is how to create a geometric model, how to create a mesh, how to apply boundary conditions and forces, and then how to get the results by solving the finite element model. Up till this point, do you guys have any doubt?
Clear, Doctor.
Clear. Okay. So in further classes, as I finish other parts, we will discuss more about the ANSYS framework, and we will also try to go into fatigue modeling in this particular case. Okay, so if you don't have any doubt, I'm going to stop right here and we will continue from Tuesday. Okay, so before I stop, let me save the entire project because we have created new model. Okay, so now everything is saved, including your model here. Then you can close it.
Doctor?
Yeah.
I messaged you through Teams yesterday and
Yes.
Thursday also.
Regarding what? Regarding what?
I asked you to add me to the other section, so I want to attend with them at the time.
Okay. Okay, so I'm lagging behind in the other section. You can attend. I got the message. I will try to add it today only. Okay.
Okay.
Is there any student in this group who does not have a group yet? Any student in this section who does not have a group for the project? Everybody has a group. Any group has the number of students 3?
I don't have a group, Doctor.
You are the person who messaged me?
No, I didn't message you.
You don't have a group. Okay.
No.
Anybody else?
Doctor, I don't have a group.
Okay, so Muat and I think Muhammad Ali, right?
Yes.
Who else? Muat, Muhammad Ali, and who else?
Me too, Doctor.
Khalil Muhammad, right? Okay, why don't you, all the 3 of you join together? There is also, I think, another person from the different section. He can join you guys as well. Okay, so just 1 second. Let me note down your numbers so that I can give that information to the other person as well. Okay, first person's name is Muwat, right? Can you give me your student ID? I think I can get it here, 20190858. Okay, let's go for Muhammad Ali. Muhammad 20192678. Let's see here again. 2678. Okay. Third person is Khalil Mohammed 20188555. Right. 855, correct. Okay, and Okay, so let me just in case check here. There is one student. I think this is the person, Mohsen. Okay, so I will add that later. Okay. Let's see. This is 2018, 2019, 8217.
So,
Okay.
Doctor, from today I can attend with them, right?
Yeah, who is this? Mohsen?
Mohsen.
Mohsen Mohsen?
Yes.
Okay, one second, I'm coming. Hussain Jafar. 1 second, I'm coming to you. Okay, so from, yeah, Mohsen, you can attend from today. I will try to add your 20195372. Maybe I should be able to copy. Copy. Let me see if I can add your name. Section 2. Okay, so I'm going to cut here and then do this. Copy. Is your name Mohsen Mohammed Mohsen Gadir?
Yeah.
Right. So it is already added. You will be
Yeah,
able
yeah.
to attend.
I've got notification. Thank you.
Okay. Okay. 1 second. There is the other group here. I want 4 of you guys to join together and create a group. Muwat Mohammed, Khalil Mohammed, and Hussain Jafar. Okay, these are the student IDs. I want you guys to start. All the 4 of you guys will be sticking together and working on the project or any other group assignments which I give. Are you there, Muwat?
Yes, Doctor.
Okay, please make a note of it. Muwat Mohammed, Khalil Mohammed. Please make a note of this group with the student IDs. Can you see that?
Yes, Doctor. I took a screenshot.
You took a screenshot, so all of you can take a screenshot and you can mail each other phone numbers or whatever and then start working on it. Okay?
Okay, Doctor.
Oh, very good. Okay, so we are done for the class today and we will meet again on Tuesday. Okay, see you guys.